No problem. That's your fast.
This inequality is where calculus begins. Okay? This is a critical inequality. Now the way it's posted here, it's a discrete math problem, right? These are numbers with n's in them, it's discretized. If we can do this, we can't get into any calculus. Now, of course, you learn some calculus in a mechanical sense. Here's the formula, here's you apply it, here why is this, here's what that, take the derivative, if it's positive, the function's increasing and all that. But formally, you can't get into any calculus without this inequality, right? And that's one of the reasons the people really couldn't get into calculus, the society as a whole. A lot of great mathematicians existed way before, thousands of years ago. They come up with quite interesting stuff, but not calculus. There was this amazing gap that got solved 200 years ago. How do we get from here to calculus? And the end result of that gap is the letter E. Now that's just a number, E, 2.70 something, but that's not our interest today, how much is E, but rather how to get to it. Now I can't do this in 20 minutes, but I want to give you something to think about, and we'll get a chance to talk about some more at recitation about it. As I said, this is super trivial, this inequality here. Can anybody remember? Does anybody remember why is it obvious? Like requires no proof at all. Yes.
It's like the same number to a higher power.
Same number, which is greater than 1, right? It's 1 point something. And this has more of it, right? This is more of that, so that's bigger. That's easy. This one, it's not easy, but somebody proved it. At least one of you came to office hours, started something. We're going to do this at recitation next week. It will take about 10-15 minutes to see how to prove this. And then this one is also not easy. I would even say this one's hard. So last time, remember on Tuesday where we at, and I didn't want to finish it, was like, okay, what I really want to get out of here is we got stuck with the logarithms, right? We said what we want to do is eventually get to the fact that 1 over n plus 1 is smaller than ln of 1 plus 1 over n. It's smaller than 1 over n. This is an amazing inequality because it bounds the logarithm, the natural logarithm, extremely tight. Imagine what happens when n is 1,000, which is not that big of a number, right? I mean, then 1,000 is a very reasonable number. In number theory, in prime numbers and cryptographic systems, they talk about huge numbers. So just n equal 1,000, right? This is the logarithm of something. It's extremely well approximated between 1 over 1,000 and 1 over 1,001. Now those two quantities are very, very close, right? The difference between this and that is very small, which means it bounds the logarithm in a very small interval. This is the reason calculus was difficult for antiquity mathematicians, for the ones from 1,000 years ago. They didn't have a way to get a logarithm in an elementary way. All right? So this is what we want to do, and once we do this, we can prove very easy stuff about harmonic series, for example. We get there. And remember what I did last time? I took a bunch of logarithms, and we all know that if I take logarithms here, I get n ln of 1 plus 1 over n. Is that clear? That if I take the logarithm of something that has a power, the power jumps into the front of the log. So what I'm saying is log of a at k is k log of a. K jumps out. Do we remember that? So I take these logs and I do that, and I got stuck. And I was asking why I get stuck. The answer is rather philosophical. The answer is I actually don't know what logarithm is. I take logarithms, I know this formula. The reason I'm getting stuck is that I actually didn't define what the logarithm is. So that's another critical point. You all know what logarithm is informally, but how do we mathematically say logarithm? And even further, how do we say logarithm in base e? How do we pick that e? What does it make it so natural? Like you say, natural logarithm is base e. Turns out e is not very intuitive at all. Who would have guessed 2.71 da da da, an irrational number? People who have guessed much more friendly numbers, right? 1, 2, 3. E turns out to be extremely unfamiliar, yet we call it natural, right? Natural logarithm. So I think the difficulty in here is that we have to get to this E story first. How do we get to E? And why that makes such a nice base? So here's that story, shrink it in 10 minutes, right? Let's imagine this. I'm going to call this here AN. And I'm going to call this, if this is AN, who is this? This is just AN plus 1, right? Because it's the same thing, but not for N plus 1. And I'm going to call this here Bn. And who's this then? If that's Bn, who's this? Bn plus 1. Of course, I have an infinite sequence here. A is infinite sequence because A 100 is going to be who? 1 plus 1 over 100 at power 100, right? And I could do this for any number, 1,000, 2,000, 3,000, doesn't matter. And I have here B100, which is who?
1 plus 1.
1 plus
1 over 100.
101 at power Bn. 100 at power 101. I can also, this is an infinite sequence. What is this inequality telling me? If I know this inequality for any n, that means B sequence is strictly, what happens to Bn plus 1? Strictly decreasing. In other words, 1 over 1 plus 2 at power 3 is bigger than 1 over 1 plus 3 at power 4, bigger than 1 over 1 plus 4 at power 5, so on and so forth. And what is this inequality here saying? A sequence is strictly
Increasing.
increasing. And not just that, what is this inequality saying now between the left and right? So A is increasing, B is decreasing, but what is this saying?
B is always bigger than A.
Every single A would be smaller than every single B, right? So the picture is, I'm skipping a step here, mathematical step, just to move on. The picture is what happens to the A's, A1, A2, A3, A4, right? It's increasing. What happens to the B's? B1, B2, B3, so far they're decreasing, yet there is a line between them. They're not going to pass this line either way. Now, can we prove that they go to the same line? In other words, how do I know that they both are convergent? That's from homework 6, right? They actually converge to something that's the same. Like, why there is no gap in here? I mean, a sequence can be decreasing and being, say, bigger than 10, and the other one's increasing but only smaller than 8. That means there's a gap 8 to 10 in between. That's not the case. Those two sequences go to the same thing.
They're going to be going, as n goes to infinity, they're going to be reaching that line.
Right. If you look at those two, they're not going to reach 1. This line is not 1.
Yeah. No, they're going to be getting closer and closer to that line.
Right. So we need to show that the gap between them shrinks down to 0. Right? It's not just increasing and decreasing. They actually get very close to each other. Now, of course, they're going to be convergent because if something is monotonically increasing and it doesn't go to infinity, it has to stagnate to some line, right? It can't go down. It doesn't go to infinity. It got to be flattened out. Asymptote, how we call it. Right? So guess who this line is? That's E. Both those limits go to E. E is right here. That's why it's natural, because those two sequences go to E. Those sequences are important. It's not easy to come up with a limit. The inside of the base of any one of those goes to, if I drive the limit to infinity, what's the limit of this base? 1 plus 1 over n, or 1 over plus 1 over n plus 1? Just the base. The limit is 1, right? Because it's 1 plus a quantity that's extremely small, it gets to 0, so that's 1. But what's happened with the exponent? Goes to infinity. So, naively speaking, 1 plus 1 over n, if you go in the limit, goes to 1 at infinity. That's why it's not clear, is that limit 1, is it infinity, or is some number in between? It turns out to be this number in between, E. So let's assume I put E there. So I'm going to say everybody here is smaller than E and everybody here is bigger than E. Right? So this whole discrete part of this exercise is I have those sequences, I get increasing, decreasing, I get the gap is shrinking, therefore there must be something common. They have the same limit. One comes from the bottom, one comes from the top. That limit we call by definition E. It's not important, it's 2.71 for now. It's whatever it is, but it's an actual number, right? There's got to be some convergence limit of those two sequences. Let's call that E, and let's put that E in here. Now, why it's in here is because this one is increasing towards E, and this one is decreasing towards E. That's why E has to be in between them. So now if I take the logs, what happens? Remember I didn't have this E last time? I didn't know what E is, I didn't know what logarithm is. But now if I take the log, I didn't know what natural logarithm is. I can define logarithm as the inverse function of the exponential. But what is natural logarithm? If I take the log, now I get what? On this side I get n log of 1 plus 1 over n smaller than log of E smaller than n plus 1 log, I'm just taking this log right here of 1, right? So I just jump the n plus 1 in the front and I get log of 1 plus 1 over n here. Now this logarithm is any b I want. I can take logarithm in whatever base I want here. So why do I want the base to be E?
That'll make the middle 1.
Because that will make this 1. The base B is nice when it's E, because I want this to be 1. If it's not E, this logarithm will be either a little more than 1, bigger than 1. So how do I define the natural logarithm? I need the base in which the logarithm of E is 1. That's the definition we're looking for. Natural logarithm, ln, is the log with base B, because we want that log of E to be 1. So now if I decided that's the log I want to use in that base, how much is this? N, natural logarithm of 1 plus 1. Smaller than this is going to be 1. That's how I pick the base to get 1 in here. And this is going to be n plus 1 logarithm of 1 plus 1 over n. Now, I want to read this inequality, it's a little different. In this one, I get ln of 1 plus 1 over n is smaller than, if I divide with n, I get 1 over n, right? And in this one, if I divide with 1 n plus 1, this inequality, I get the logarithm, natural logarithm of 1 plus 1 over n is bigger than 1 over n plus 1. Everybody sees that? That's just an arithmetic manipulation. If I divide this inequality with n, I get the natural logarithm of 1 plus 1 over n is smaller than 1 by n. If I divide this inequality with n plus 1, I get the same quantity, logarithm of 1 plus 1 over n, bigger than 1 over n plus 1. So now if you put those two together, what do I get? I get this log that I was bugging you for weeks with it. The natural logarithm of this quantity, it's bigger than 1 over n plus 1 and smaller than 1 over n. So that's the inequality we need for logarithms, right? So those two means L of 1 over n plus 1 smaller than 1 over n is bigger than 1 over n plus 1. This is critical to move to calculus. And it comes from these two sequences that are one increasing, one decreasing with a common limit e. Now, once I have this, I can do very cool things with it. I can say 1 over n plus 1 is smaller than ln. This is n plus 1 divided by n, right? Obviously, inside there. And then I know the logarithm of a fraction. Logarithm of a fraction is? Subtract who from who?
N plus 1.
N plus 1 minus ln of n, right? Right? Now suppose I sum this up for all the n. So I do summations. So I do sum from n equal 1 to say z, some big z, right? Of 1 over n plus 1 is smaller than the sum of n equal 1 to z of ln of n plus 1 minus ln of n. It's smaller than the sum of n equal 1 to z of 1 over n, right? I just take this inequality for n equal 1, 2, 3, 4, 5 up to z, and I sum up all the parts. Right? Because if this is more than this, the sum of this is smaller than sum of that, smaller than sum of that. Now this is that interesting telescoping series, right? If you actually think about what this is, what's going to happen here in this sum? If I really am to write this down, this is ln of the first term is who? Ln of 2 minus ln of 1. The next term is 3 minus ln of. So if I plug in n equal 2, what do I get here? 3 minus ln of 2, right? The next one is ln of 4 minus ln of 3. And the last one is ln of
Z plus 1.
Z plus 1 minus ln of z, right? Huh. And what is this? This is 1 over, starts from where? 2 plus 1 over 3 plus 1 over n plus 1, right? And what is the other stuff? 1 over 1 plus 1 over 2 plus 1 over n. So this, I say, this is the harmonic term that we defined last time, hn plus 1, but it's missing the 1. It's, the harmonic was 1 over the inverses up to, at some point, but it includes the 1, right? It's 1 plus 1 over 2 plus 1 over 3, so on and so forth. This is exactly that. So what do I get here? How much is, this is telescoping. This goes away with this. This goes away with that. Right? This goes away with this. What am I left with? ln of 1 is what?
0.
So what is this out of this? This is ln of z plus 1. This is hz, right? It goes to z plus 1. So this is between the harmonic terms hz and hz plus 1 minus 1. That immediately shows you how tight the harmonic sum is to the logarithm. When people say approximate the harmonic sum with the logarithm plus a constant, you can see that from this inequality. The harmonic sum is very, very tight to the logarithm. In fact, the difference is convergent to a fixed constant, 0.58 or something like that. That's it. Isn't that cool? Pretty cool, huh? Yeah. What I showed you last time was this notion with integrals. If I integrate this function, I know how to integrate this because I only need the primitive of it, the function that differentiates to that. And I apply the formula if the delta f at delta x is f of x, right? If the differential of f is f, then the integral from 1 to x t x of f t dt is f of x minus f of 1. This is the fundamental relationship between differentials and primitive functions. If the primitive function differentiates to f, then you integrate f back to the primitive. Right? I think you've done this in calculus. So if I know the primitives of this, I can integrate the functions and get the same relationship. That's what I showed you last time. And it's easy to tell which ones are the primitives. We know exactly what function differentiates to this, what differentiates that, what differentiates that. You know, it's a table. Why I said that's a chicken and egg thingy? If you do the calculus proof, you run in circles. Because to show anything with calculus, including differentials and integrals and whatnot, I need first logarithm and the e number. So it's a little bit of cheating to say I'm going to use calculus to prove this because I would have no calculus if I couldn't prove that to start with.
Well, can't you just do derivatives with limits though? Why do you need log stuff?
Can you do derivative without limits? You mean?
No, you can just do derivatives with limits. Does that require logs?
Yeah, but the primitive function of this requires the log,
Oh, for that, yeah.
right? I think there might be ways to go around the approximation, but effectively you don't have a limit until you prove that. And the right formal way to do it is with discrete math, because we don't have anything other than discrete math before we get to the limit. All right. That being said, let's figure out this midterm again. I have another cool thing that I'm going to do at recitations. There's something in your recitation that says these inequalities, and it says it's easy to do with convex arguments. I want to do one of those problems as an exercise for the midterm with induction, so we can get how difficult that is. So I'm not going to pose the whole inequality set again. Those are important the important averages that you should know. The inequality in your recitation paper says the quadratic average is bigger than the arithmetic average, is bigger than the geometric average, is bigger than the harmonic average. Now you should know what those averages are. If somebody talks to you about the quadratic average, you should know what that is. I'm sure you know what the arithmetic average is. That's how your grades are computed. And there's a harmonic average and geometric average. And the inequality states the order is that one. I'm just going to say, how about we just deal with quadratic a1 squared plus a2 squared plus an squared by n. That's bigger than, the arithmetic is what? Can we prove this by induction? By induction, we say last time, well, what would this do? Will mean I have to do an induction step. So I'm skipping the text of the problem. Induction step would be the square root of a1 squared plus a2 squared plus an squared plus a plus n squared by n plus 1. Actually, I'm not sure we did this or not. Did we finish this? We started it? It would be bigger than an plus a2 plus an plus 1 by n plus 1. So an induction proof will say, if you know this, then you could do that. This is still a weak induction, right? If I post it this way, it's from n to n plus 1. This is not for the meter. This is more difficult than the midterm is, okay? You should not expect something that's in the midterm because it's too complicated. But what you can try on the side is to say, forget about induction. Can I just prove it for 3 things? How does it look for 3? A1 plus A2 plus A3 squares divided by 3, right? Square root is bigger than A1 plus A2 plus A3 divided by 3. Right? This was proposed for the midterm. Was that close to get in. But it didn't. There will be no point doing it now. Not as an induction proof. This is not an induction proof. There's no induction here. Just proof for any A, B, C. This is happening. With the condition that all AIs are positive real values. So we don't want to deal with negative ones. How would you prove something like this? This is not an induction proof. This is an induction proof to do it in general. From 3 to get to 4, from 4 to go to 5, so on and so forth. But say I say, I want to prove this for any 3 numbers. What do I do? Let's play a little bit with it. Yes?
Square both sides.
Get rid of the square root, so that's A1 plus A2 plus A3 squared divided by 3 has to be bigger than A1 plus A2 plus A3 squared divided by 9. Now what?
Now that's we expand the.
Let's move the 3 with 9, remains a 3. Move the 3 here, I get 3A1 squared plus 3A2 squared plus 3A3 squared. Bigger than, you say expand this, what is it?
We get A1 squared plus A2 squared plus A3 squared. Plus.
It's minus 2A1.
It's minus?
I don't think it is.
So everybody gets what I got this 3's here? Once I got rid of 3 with 9, I still have a 3 here, which I move in here. So it's 3, orange, apple, and, you know, watermelon. And then how do I expand this A plus B plus C squared? I got the squares, but then what comes after? 2A1, A2.
Plus 2A3.
A1, A3 plus 2A, 2A3. And now I got some squares that I can get rid of if I want to. So if I get rid of these squares, every one of these becomes a 2, right? So now I have 2A1 squared plus 2A2 squared plus 2A3 squared bigger than A1, A2 plus A2, A3 plus A1, A3. And now what?
The 2's.
Divide by 2.
I can divide by 2. Is that going to go somewhere interesting?
It's.
Everybody can see there's a bunch of 2's here. I can get rid of them. But do we have, see, is the pointer that I have an eye on the ball and I need the other eye on the target, right? Where am I going with this? That's actually a huge point for this midterm. You won't get the problem that difficult in the midterm. Problems will be easier. But you should first take a minute or 2 to make a plan that sounds sensible. Don't go into a formal writing solution sort of mood between you get a sense of what do you think the answer is, how to approach it. Because the biggest problem by far in this midterm is going to be the time. If you don't get an A in this class, it's going to be because you didn't finish this midterm. No other reason. Trust me. So you're going to know how to do the problem. I know some people, I heard people were crying at homework 6. That's not true, right? This is just people who want to scare other people off. The midterm's easy. But you may run out of time if you try writing something very formally before you know it's right. So don't bother too much with formalism before you get to an answer that makes sense.
When did we get rid of the 3 in the denominator on the right?
9 and 3 went away, I still have a 3.
Yeah.
But this 3 when I move here becomes 3 times A1 squared, 3 times A2 squared, 3 times A2 squared. The 3's that I cut later on when I got rid of this. Okay, so make clear about this point. The midterm, as fast as possible, get to a reasonable sense of the answer. And when you think that's right, verify it, and only then start writing it up. Okay, how does Virgil wants to see this? Oh, he needs the induction step. Oh, he needs the base case. Don't bother with all of that until you get the sense that you're right. And another thing, start with the easy problems first. Don't worry about the order in which they are written. The one that you think you can do first, or it's most obvious from text, or whatever, do that one first. But do it in a way, if you can, that you don't have to come back to it. Another mistake that people do is to do something quick and say, oh, I kind of get that one. I'm going to look at it at the end. There is no such thing. Look at it at the end. So if you get something done and you're confident about it and you know this answer, you take right there the time to verify it, build a truth table that verifies your formula, whatever it is that you verify, and put a big check on it, green. That one, I'm not going to look at it anymore. I'm going to submit it as it is. Even if the guy next to me says, hey, you got it wrong. No, he won't say that. Don't look at it again. I got it in the bag, it's good. You can put some question mark on some things. Hey, I didn't finish this one. If I have time, I'll look at it. But the one that's in the bag, put it in the bag for good. Because you won't have time at the end to look again at it. Now back to this. What do I do here? Anybody has an idea what to do here to get to the answer? Yes.
Move all the things on the right to the left.
Move everything here, and then a1 squared, 2a1 plus 2a squared plus 2a3 squared minus 2a1, a2 minus 2a2, a3 minus 2a1, a3, right? Then what? Bigger than 0? Is that right? No? Can I do something here? Yes.
Can you do like a1 squared plus a1 squared plus a2 squared plus
a1 squared plus a2 squared?
No. So like, you know how there's two a1s? So
Yeah.
like separate them?
Those two?
No, like so.
Yeah, I separate them. I got an a1 squared, and
Yeah.
then later on I got another a1 squared.
Right. So then write that, right? So then.
How about I take an a1 and a2? I separate, like she says, I take an a1 and a2 squared, and I pair that up with 2a1, a2. Then I get the other a1 squared now paired up with a3 squared minus 2a1, a3. And then I got a2 squared plus a3 squared paired up with 2a2, a3. That has to be positive. Now how much is this?
A1 minus A2 squared.
a1 minus a2 squared, 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 positive. There are many ways to go around do those things. But that's a problem you're going to have in the midterm, not this problem. I have this ball, okay, and I know where the target is. How do I get from with this ball down to the target? I need to make some steps to get there. In here, the target is a little difficult because bigger than 0 is not an easy achievable target. You're not going to have this. You're going to have something equal with some formula. Okay, so let's do some other stuff that I've seen there in midterms and other exams. But my point of recitation will be, I can solve these inequalities with something called convexity, which I think is new for most people. Let me just say what it is without any explanation. This is what we're going to do at recitation. If a function looks like this, it's called convex. It has the property that if you take two values, every time you average the two values, you get bigger than if you take the average and compute the function. See, this here is bigger than this here. A function is called concave, is the opposite. If it has the opposite effect, anytime you take two values, if you take the average, you get a bigger value if you do the average first. So this is x1, x2, this is f of x1, f of x2, This in here is f of x1 plus f of x2 by 2, the average of the two values. And this in here is the function of the average. It's concave if it's like this, between the values it's bubbling up, and convex if it's bubbling down. The property of convex function is an entire branch of mathematics, convexity. It has huge implications in data sciences because machine learning algorithms, for example, they work much better when their objective, their target is convex than when it's not. We know much better how to optimize for convex functions, both in terms of quality optimization, but also the speed. You can get much faster. A convex function, you can see why. Getting to the minimum of this function is really easy, right? It's only one minimum. Mathematicians have figured out 400 years ago how to get to it. As opposed to a function that looks like this, find me the minimum of this. That's tough, right? You can see why a convex function, if you say find me minimum or maximum, even though we don't know the mathematics to do so, it's probably not a hard problem. So in machine learning, when they try to optimize a neural network to find out the next word you're going to type, for example, or what's in the image, or anything like that, dealing with convex function makes the problems a lot easier. So this is a branch of mathematics. And this, among other things, will answer all these inequality questions immediately if you know how to manipulate convex functions. So that's something I'm going to do next week. Let's really get back to the midterm. Here's one, I equal 1. I'm going to try to go fast, see what happens. Right, I equal 1 to n of k, everything squared. Don't be confused between everything squared and just the k squared. Is equal with sum of I equal 1 to n of k cubed. Let's assume that's true. I mean, I didn't verify it, but I think it's true. So, okay, if this is an induction problem, right? So, how do we write an induction step? The sum of I equal 1 to k, sorry, this is a k, right? Okay. K equal 1 to n plus 1 of k, everything squared, is the sum of k equal 1 to n plus 1 of k cubed. Fine. So how do we prove this step? All induction proofs require a relationship figured out between the next guy and the previous guy. So now you can treat either one, you can tackle this next thing from here or from there. Or you can try to manipulate it a little bit. Before you say, okay, before I get to what I actually want to prove, I can derive this a little bit to see what is that about, if I want. Where should I take it on? This end or this end? Left side? Right side? You want right side?
Left.
Right side. Left side?
Left side.
Let's do the right one, because the right one seems easier to. What's the relationship between this guy and its analogous for just n? What happened from here to here? I just added a term, right? That one is a little bit more tricky, right? This one is just added a term. I added a term, but then everything got squared. So it's like taking the square root, add a term, and then square it back. It seems more complicated than just adding a term. So that sum, k equal 1 to n plus 1 of k cubed, is the same sum from before, plus what term got added? N plus 1 cubed, right? And now I'm going to use the induction hypothesis to say, okay, I know who this is from my induction hypothesis. That is the sum from k equal 1 to n of k, everything squared, plus this new guy, n plus 1 cubed. Right? And I'm going to put here equal, that's my ball. That's my ball I want to work with. And what's my target? My target is, I started from the right side, so my target is the left side, right? If I started from the left, my target would have been the right, because my purpose is to show those two things are equal. So I'm going to say equal with k equal 1 sum n plus 1 of k square. That is something that I don't know. This is something I know from the induction premise. Induction premise is as good as anything to use it. You can use it as I know it, but this is something I don't know, so this is a question mark in here. So now I'm going to play the game with the balls and the target by playing it out to see what happens. So I'm going to leave this for now this way. Sum from k equal 1 and k everything squared. Plus I'm going to open the parentheses here. How much is n plus 1 cubed?
N cubed plus 3n squared plus 3n plus 3.
3n squared plus 3n plus 1, right? And now I want to break this, open the parentheses, but I want to treat this as a plus b squared. So this in here, it's in fact that sum, right, is the sum from k equal 1 to n of k's plus, what's the next term, n plus 1, right? Everything squared. So I have a sum that I want to leave alone. I don't want to play with it too much, just as an object in itself. And then I have this other a and b squared. So I'm going to get this sum here, k equal 1 to n k everything squared. I like this because it's the same as that when it's going to come out of the square, right? Plus n cubed plus 3n squared plus 3n plus 1 equal with that sum squared. Plus n plus 1 squared plus 2 this sum right, times n plus 1. Because the formula for the square is a squared plus b squared plus 2ab. So I got a squared plus b squared plus 2ab. Now I cut this off with this off, right? I got n cubed plus 3n squared plus 3n plus 1 equal with n plus 1 squared is n squared plus 1 plus 2n. And now I have to know a formula here. Sum of the first n integers. How much is it?
N plus 1 over 2.
N plus 1 by 2 times n plus 1. Okay, so what do we have? Actually, looking back, I would have been better to keep this as n plus 1 cube. I think that would have been easier. Because everything seems to have an n plus 1 in it. I can reduce that, but now it's too late. I'm in the exam. I wrote this up. Better finish it like that than go back and make a mess out of it. Right? So, n cubed plus 3n squared plus 3n. I can get rid of at least those ones here. Equal with, I have an n squared plus 2n. 2 goes away with 2. And I got n times n plus 1 squared. That is n squared plus 2n plus 1. Is that right? Okay. I can reduce an n. Everybody has an n. I can get rid of that. N squared plus 3n plus 3 is n plus 2 plus n squared plus 2n plus 1. Right? I divided everybody by an n. So now let's see. 1 plus 2 goes away with 3. Right? N squared goes away with n squared. And 3n. So I'm good. If you find yourself with this kind of regret, I open these parentheses. Would have been nice to not open them because I can see another route doing it. I think you should also evaluate, does it worth erasing, cutting, yet another page, write it again, or just slow it down, you know, like go down with it. Maybe that's faster than just, even if you found a different idea of doing it, it may cost more time than just finish it up the way you started.
When we're doing induction proof, like what things do we need to label? Do we need to label the conclusion that we're doing? Like,
So you have to write the induction step first. It has to be clear. I would like you to write, in this case, n to n plus 1, right? To be clear. And then you have to write the proof on the induction step. But don't forget about this want sign, either the word want or the question mark. I did forget in here, right? So this is really, I want, down to when I get to true, so we're good. All these cannot be equal signs because they're not equal. You don't know them. You want them to be true. In complicated, when you see the equation being messy, trying to do it this way, start with that must be equal to that, therefore that must be equal to that, so on and so forth, might be easier than just trying to figure out where the ball needs to go without matching the other side. Because in here I have the ability to cut things both sides. It simplifies faster to something true. Okay. How about this one, another reduction problem. A0 equal to an plus 1 is 2an minus n. So that's a recursive definition, right? Because it involves this an in it. The next guy is not just a formula, it's something to do with the previous guy minus n, right? So Fibonacci was a little bit more advanced. Fibonacci had to do with the next one was the dependency of the previous two, right? Was the previous one and the one before. This one is part in clear, in closed form, this n, and part depending on who the previous value is. Now we got to prove that, so that's a definition, prove that an is actually 2 to the n plus 1. So that's a closed form. Right? It doesn't have any dependency of an minus 1 on anything else. Like this one is a recurrence because it depends on the previous one. That's a closed form. Now that's given. A problem like this can be a lot more difficult if the formula is not given. If it says, find the closed form. That's a lot harder than, here's the closed form, you just get to prove it, right? So how do we prove this? By induction. So what's the induction step? From n to n plus 1. That's what I have to prove. So what am I going to write here? Remember, the induction step is an implication, right? If something, then something else. What do I get to write? What is the premise and what's the conclusion of this induction? This is given to me, and this is what I'm required to prove. This is for all n bigger than 0, I guess. What's the induction step here? So what am I proving? This is not the sum of terms, right? I'm not trying to prove the sum of the first terms, yes?
Would it be that a sub n equals 2 to the n plus n plus 1 implies a sub n plus 1 equals 2 to the n plus 1 plus n plus 1 plus 1?
Yeah. Very good. I'm going to prove by induction that that's the correct formula. Okay? So how do I do that? I start with my new customer, right? Who's my new customer? An plus 1. Who is an plus 1? Yes.
2an minus n.
I apply my recurrence definition to an minus n. So now, what do I do the next step? I know who an is from where? From the induction premise. So it's 2 times 2 to the n plus 1, right? This an is this one, minus n. So what is this? 2 to the n plus 1 plus 2n plus plus 2 minus n. So it's 2 to the n plus 1 plus n plus 2. Am I done? I proved the induction step, aka if the formula holds for A100, it's going to hold for A101. But I didn't prove it just for 100. I proved it for all steps. So the base case, it's a simple verification because it's already given to me, right? A0. So I say A0 is given to me is 2. I have to verify. I'm going to put a question mark here. What do I have to verify? That 2 is equal with what?
2 to the 0 plus
2 to the 0 plus,
0 plus 1.
is that true? So I'm done because this is weak induction, n to n plus 1. Once I decide to start at 0, everything is going to follow after that. Here's another induction proof that you have in your recitation paper. So some of you might have looked already at it. Every student will get same grade in this course. You've seen this problem in the recitation paper? Is it given with a solution, right? Right. So here's the proof. So the statement is for n students. Class of n students. So the statement is induction step, n goes to n plus 1. So I'm going to say solution here to not confuse the proof with the induction step proof, n goes to n plus 1. If a class of n students all get same grade, then in a class of n plus 1 students all get same grade. Proof of the induction step. Take the n plus 1 students set, that would be S1, S2, up to Sn plus 1 students, right? Those are my students. I create two subsets. One is S1, S2, up to Sn, and the other one is S2, S3, up to Sn plus 1. So they all have all the students except one. This one missing one student, that one missing another student, right? This set in here is all the students except the last one. This set of here is all the students except the first one. I say apply induction hypothesis or premise. Can I apply it? Is this a set of size n now? Right, this will be same grade. This will be same grade. Right? Because by induction, I can apply this statement to a student of n, subset of n. Now, there's an intersection. If everybody here gets a D, not D, right? Let's say an A. If everybody here gets an A, and everybody here gets an A, there is something in between them, right? So S2, S3, so on and so forth, up to Sn are in both sets. So if this is same grade, let's call it G generically, and this is same grade G prime, then because those guys are in both sets, that means G has to be equal to G prime. Because S2 can only get one grade in this class, right? So these guys get the grade, these guys get the same grade, but if somebody in between, in common, that person will make sure this grade is the same as that grade, is the grade of S2. That means all n plus 1 get the same grade. Good, I'm done with the induction proof. Now I have a base case. Base case is n equal 1. Okay? One student gets, can I say same grade in logic? Can I say in a class of one student, everybody gets the same grade? Is that the correct statement? Right, it's only one person. Are you happy now? Everybody's going to get the same grade? Presumably there'll be an A. So how many people know where this is broken? Hands up, who knows exactly where this proof is broken? But exactly, I mean, you can point out down to the commas, this is broken, because a lot of parts in this proof work out just fine. There's one place that's broken. Because, let's be honest, not everybody will get the same grade. We know that already. So this proof cannot possibly be correct. So I don't want to give the answer, okay? And I don't want you to say it, but I want everybody by 6 p.m. to figure out where is this proof wrong. It's got to be wrong somewhere. And as you can see, a lot of things make a lot of sense. So it's not broken everywhere, but it's broken somewhere. So you guys get to figure out where is it broken. This is in your recitation paper, so if you figure it out, helps also writing it down for the recitation next week. I want to write this because we're recording, you know, people are going to see on YouTube, look what kind of proofs I've done in this class, right? So we want to permanently stick that on YouTube. Three, whose complement is also a 3. What's complement? Yes.
You take a complete graph and you minus all the edges that are in the previous graph.
So the same vertices, but every edge that's in the graph, it's missing in the complement, and every edge that's missing in the graph, it's in the complement. How many people know what the complement of a graph is? Again, how many people know what the complement of a graph is? I keep the vertices and I reverse the edges. Now I want the 3 that when I drew the complement I also get the 3. What do I do? Yes?
Single vertex. I mean, that's true, isn't it?
That's true. Why is that? How many possible edges are in this graph? If I have one vertex, total number of possible edges is 0. This one has 0 edges, therefore this one also has 0 edges. The sum of the edges, if this is n nodes, happy now? If this is n nodes, so if this is n nodes, how very many edges are here? Let's call it the size of E, and this size of E here, that's E complement, right? What do I know about those two sizes? How many edges? Every edge is either there or there, right? Because every edge here is missing there, missing here. So how many total edges I get if I have n vertices? How much?
N minus 1.
N minus 1 total, not in a tree, in the general graph.
So
In a graph with n vertices, what's the maximum total edges that I can get? Yes.
n by n plus 1 over 2.
N by n plus 1 over 2. Is that correct? Yes?
Isn't n minus 1?
N times n minus 1 over 2. You asking? Is that correct? Or you know the answer?
I think it's that.
Okay, so see, that's where we get into the exam. It's only 120 minutes, right? So if we think too much about how much is it, which one is it? Let's say that one. Okay, so now I can't do his example because I need 2 vertices. Can I draw it more than 2 vertices? Yes.
3 vertices.
3 vertices like that,
Yeah.
and like this.
No, draw 1 edge.
Well, that's not a 3, right? If I only draw 1 edge, it's not a 3. Yes.
Do 4 vertices, and then connect the left one with the bottom one.
These 2?
Yeah, and then make 1 connecting. Yeah.
Uh-huh. And now if I draw the same vertices A, B, C, D, A, B, C, D, what's the complement of this thing? A, B is not there, right? B, C is not there, but who's there?
AC.
A, D? B, C is there?
No.
No. B,
AC.
A, C,
And then
and B, D. Is that a 3? Uh-huh, good. And any other example? Can I draw one with more than, how many 4 vertices I have here? Suppose I want one with 5 or 6 or 7 or 11. Why is not possible?
You just set up an equation where you have the total number for complete graph minus the number of edges in a tree.
In a tree, how many edges are here? That's what you
So,
mean, right?
Yeah. So you would say you would have to find an n where n minus 1 equals the n times n minus 1 over 2 minus. N
How much this have to be if this is a 3? That has to be equal to that, right? So that's going to restrict immediately what n needs to be. If this I have a 3 n minus 1 edges, we know that, right? A 3 n minus 1 edges, you don't have to prove this kind of stuff that we've done 20 times in the recitations in the class and in the book, right? Then there's only one n that will verify this. Now you still have to draw that 3, but it only works for an n-equal form. Here's another problem here. Ten people play basketball. Out of order. I'm not saying these are easy or hard problems. How many ways to play 5 versus 5? Basketball teams have 5 players in them, right? So I have 10 people, they're going to play basketball in the backyard. How many ways can they create the teams so that those 5 play with those 5? Easy question, right?
Just
10 choose 5. His reasoning is those are the people select people for one team, and then the remaining ones play the other team. Is that correct? You guys know because we talk about this after the review session, right? Why is this incorrect? Yes.
If you choose these 5 people, there's a possibility you choose like the other 5 people in a different.
It's double counting. One selection is choose those 5, A, B, C, D, E, versus the rest. But then later on you choose the rest 5 to place against those. So every way of playing the basketball game has been double counted because I selected one team, left the other one unselected, and then later on I say another way to select is select the other 5, and then I'm playing the same teams, just call them selected versus unselected. So the right answer is divide by 2. What if I say one team, they play 5 versus 5, so this is a variant, red team versus blue team. So I say, in how many ways can they create the red team of 5 versus the blue team of 5? Now what? Now it's 10 choose 5. Because who goes in the red team versus the blue team, it matters. I just created teams IDs. Every counting problem immediately asks 3 things. Number 1, what has IDs and what has not IDs? 100 candies go to Halloween. Those candies have ID? No. 100 songs go to a playlist. Do songs have IDs? Yes. 10 people play basketball. Do the people have IDs? The people, the person 1, person 2, person 3, or they just 10 identical people? The first thing is, the teams have IDs? If I ask it this way, the teams do not have IDs. If I ask it this way, the teams have IDs, right? 17 balls go into 5 bins. Do the bins have IDs? Yes. Yes. First question is, what is distinguishable, as in has an ID? What is not distinguishable, as in they all the same? The second question is about?
Does the order matter?
The what?
That's the second question.
So the first one is what has IDs and what not. The second question in counting is?
Does the order matter?
Does the order matter? Is my answer order specific or not? If I permute the order of my answer, do I get the same answer or do I get a different answer? Does the order matter here when I select 5 people? No. How about the playlist of songs? How about the bag of groceries? How about the Eulerian tour in a graph?
Oh, tour, yes. Cycle, no.
The second question is what matters in terms of order? Is it asking me in order or out of order? And the third question is what kind of method, if I'm stuck, seems to apply? We didn't study that many methods, so we have cases, product rule, sum rule, inclusion, exclusion, combinations, and permutations. There are only like 5 things, right? And balls into bees, let's say the 6th one. So if you're stuck on a problem, you can go directly to 6 things and say, hey, which one out of the 6 things seems to be the most applicable here? You probably won't get stuck. The problems are really designed to not get you stuck on how to start. But if you do, it's not too hard to guess, okay, out of the 6 methods I learned, which ones? Actually, in graph theory, that's even easier. We only done 3 theorems, right? So if you get stuck on a problem that you have no clue how to start on graphs, go back to the 3 theorems and say, okay, which theorem seems to apply here? Okay.
What are the 3?
I made up the number 3, I don't know. They work? I think you should recap to see. I think we did something with handshaking lemma.
Yeah, handshake, that was
The
one.
sum of the degrees is the highest number of edges, right? Number of edges in a tree is n minus 1. Then we have some corollary with if there are an odd number of vertices, one of them must have hidden degree.
Yeah.
So I think you should go to that list and have a mental note on them, just in case. I think the right way to do is to not get stuck. You see a problem, you have an idea of how to start it, definitely start it that way. If you have no clue how to start it, it makes sense to go back and see which one could be it.
Some degree is so in all then you have to have some number of degrees per one that makes the degree sum.
It's like not the degrees is 2 times the edges.
Right. You can't have
That's more specific.
Try to corollary.
Now we're going way back to our childhood. So, I know this is the easiest part of the exam, sets, right? Most people make mistakes on the notation. They put the round bracket instead of the curly bracket and you lose points that way. Easy, right? Cartesian products, pairs are in the wrong order. They're not the right number of pairs. They're missing one or two pairs because they rushed up. So people make mistakes that way. One thing that's good about a set, even though what this looks like here, x, z's with property that x is 2n, what is that? That's the even numbers. It's good to actually, since this is enumerated, try to enumerate that one. What are the even numbers? 0, 2, minus 2, right? Is it z or n? Z. 4, minus 4. Just having it down on a piece of paper might help later on. I'm not saying in this problem. Sometimes when you work with a set that's written in enumeration form and another one that's written in a predicate form, you can get confused. So these are the even ones, right? So that's 1, minus 1, 3, minus 3, 4, minus 4. If this question says, I want to know who B, what did I say? A intersect B is.
4 is not an even number. 4 is not an odd number.
It's not. I will lose some points in this exam. So if somebody says what's A intersect B, might be easier to see it in an enumeration form, right? Because it's all visual here. You probably, even if you have the time, you're not going to actually spend the time to really think about this that much. You're going to apply a visual mechanic because it's a very easy question. And then having it in front of you what the sets are may make that easier. So A intersect B is what?
2.
2. And A intersect C is?
Just 1, 3.
1, 3. And B union C?
All numbers. All
That's all Z. It's X in Z, right? And who's B union C bar? What is this in English? Complement of B union C, right? The bar is the complement. The complement translates into the universe minus B union C. Minus, I think we did minus this way. Be careful of this universe. You have to decide what's the universe in here, right? If sometimes the universe is stated, maybe the problem says universe is the whole Z, all the integers. Then in that case, how much is B union C complement? Empty set, right? Because it's that. But what if the universe is all the real numbers? Now it's not the empty set. My point is, when you deal with complements, take a moment to not to answer exactly what the complement is. Whenever you see this bar, your first question should be, what is the universe in here? I'm taking the complement with respect to what? Because all complements are taken to the same universe. So once you say the universe is the real numbers, all complements are going to be against the real numbers. But sometimes this may not be immediate, you know, because it's easy to say it's the empty set if the universe is indeed the Z numbers, right? If it doesn't say anything, it's probably the bigger set you can imagine here, the integers, right? And what is A intersect C? Product, Cartesian product with A. A intersect C, we already said is 1, 3, and A is 1, 2, 3. So how do I write the Cartesian product here? Between 1, 3 and 1, 2, 3.
1, 1, 1, 2.
1, 1.
1, 2. 1, 3. 3, 1. 3, 2.
What? 3, 2?
Oh.
The key in here is mistake?
I just had a question.
Yeah.
So when you're doing Cartesian products, the order in sides matters, but when you're doing power set, it doesn't matter, right?
So the order, these pairs are elements in here. I could write the pairs in a different order. I could say 2, 1 goes first, 1, 2, sorry. 1, 2, and then 1, 1, and then so on and so forth. They are elements. I can write them in different order. But the pairs themselves, they are not swappable.
Yeah.
Like this 1, 2 is not the same as 2, 1.
But in a power set, you can swap them, right?
Well, those are not pairs in a power set.
Right, but when you're doing groupings.
Right, so I have here a question about that. What is the power set of A intersect C? Power set of the set, what is it, 1, 3? What is that? What's the power set, first of all? The set of all?
The set.
So here's the big set, B subsets. What subsets are there?
Empty set.
Empty set. Every element here is a set. So that's 1, and then another one is 3, and another one is 1, 3. I think what you're asking is about this. Now this being a set, I can swap the 1 and 3, it's the same set. But this here is a pair. If I swap the 1 and 2, that's a different pair. A pair is in order, it has round brackets. A set is out of order, it has curly brackets. How about in here, in this example, the power set of the power set of A intersect B? Who's A intersect B? So you build it little by little, don't get scared. This in here is the power set of, what's power set of 2? Is the empty set and the set of 2, right? So I have a set with 2 elements. One is the empty set inside, and the other one is the 2, right? That I did the power set of A intersect B. It's a set of subsets. And now I have to do the power set of that. This has how many elements? 2. So how many elements the power set is going to have? 4. Which ones are those?
The actual empty set.
The actual empty set.
The set of the empty set.
The set of the empty set.
The set.
I need to look at the papers because I would get it wrong.
The set of 2 and the set of the empty set.
Is the set of 2 or the set of 2?
The set of 2.
Yes, it is wrong.
A set of
What is this one?
the set of the empty set.
What is it right?
Oh, okay.
Yeah, and then the last one is the set of
And then the set of empty set.
So the last one's gotta be the empty set and the set of 2, right?
yeah.
That's the set of
So this one is who?
It's a set of the set of 2.
Yeah.
That's a great question to ensure half of the students get it wrong. No matter how smart you are, some of them will be wrong. Exam from the previous year. There was one here I wanted to do.
We have.
No, here.
Local's great. Local makes everything so easy. It's literally completely all no.
I have a formula. It's A or B or C
I thought you were flexible.
and not A or not B or not C. And I'm saying a satisfying assignment, it's something like A equal 0, 1, B equal 0 or 1, C equals 0 or 1. So if an assignment means make A, B, C equal with something such that the whole formula becomes true. Satisfying assignment means what the values, Boolean values A, B, C do I need to get it true? How many? Satisfying assignments. How many different satisfying things? How many ways can I set A, B, and C to get this formula to be true? This is a counting problem, but the whole support for it is in formula and logic, right? I'm not asking what are the satisfying assignments, list all of them. I'm not asking list one satisfying assignment. I mean, you can list all of them if you want to count them. I'm asking, how many are there? So one way to do it if we have no clue is truth table, right? A, B, C. How many options are there? 0, 0, 0, 0, 0, 1, da, 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 da. How many? 8. Now in here I have the formula F equal A or B or C and not A or not B or not C, right? And then I get a bunch of things. What is this asking me to count in this table?
How many were?
How many? Ones, right? Every time I get a 1, if this is a 1 here, I'm counting as a satisfying assignment, right? Every other 1 is another satisfying assignment. So how many satisfying assignments are there? If I build this truth table, that's a brute force solution. I'm just listing all the cases, counting the ones. That's going to give me a count. Is there an intelligent solution here? Which one is it? Because see, the thing with the truth table, it works for 3, but what if I put 6 variables? A or B or C or D or E or F versus not A or not B, right? I put 3 more. If I do a truth table for 6 variables, how many rows I'm going to have there? 64 rows. That's quite a lot for an exam.
Maybe for you.
Somebody has an answer, somebody else, yes.
You can say there are 2 to the 3 possibilities and only 2 of them don't work.
So this is all minus invalid. Which ones are the 2 that don't work?
All of them are true or all false.
True, 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 false, false, false. We need 1 to be true and we need 1 to be false. Therefore, when all of them are true or all of them are false, it fails. Any other case works. So it's the total number of possibilities, that's 2 to the n if I have n variables, minus the invalid possibilities, which are all true or all false, 2 of them. That's the answer. Okay. What else? License plates have 6 spots.
Yes.
First 3, there's gotta be capital letters. And these gotta be digits. And the capital letters have to exclude three particular combinations or sequences. So I'm saying all possibilities of capital letters are there except 3 that are given to be not possible. Things like EIP, XYZ, and XAX. Those 3 are not allowed. Everything else is allowed. How many license plates are here? Somebody else. How many license plates total I have here? So I get 3 letters, 3 digits. Everything is good except the 3 letters. I have 3 sequences that are not allowed. Order matters here?
Yep. Yeah.
Or not? Matters. How about those letters? They clearly have IDs, right? A, B, C, D. How many letters are there?
26.
Capital letters? 26. How many digits?
9.
10. Let's say 10. Right? And that's how many license plates I have?
26 cubed minus 3 times 10.
26 cubed minus 3. That's all the way to put the letters.
Times 10 cubed.
Times 10 cubed. That's all the way to put the digits. Did I count anything twice? Is it possible to obtain a license plate in 2 ways? Did I count every single license plate that's possible? Is there any, except those ones that are not allowed? I can't get VIP 1, 2, 3 because that's not allowed and I'm not getting it, right? But he understands where this is coming from? This is a product rule, right? I have 26 options, I have 26 options, I have 26 options. That's all of them, just like in here, but I'm excluding the ones I know are not allowed, the 3 ones. And then for every combination of letters, I get any combination of digits I would like. How many cards I have to draw from the standard 52 deck? We all know what that means. Standard 52 deck of cards. Cards have a certain organization. They have suites or colors, and in each color they have how many values? 2, 3, 4, up to 10, and then Jack, Queen, King, Ace, right? To guarantee, to ensure, what is it? 3 cards of same value. So the 52 deck is 4 suites or colors times 13 values each, right? And make sure everybody knows what the deck of cards is. The suits are clubs, diamonds, hearts, and spades. And the values are 2, 3, 4, 10, Jack, Queen, so on and so forth, right? So how many cards do I need to draw to make sure I have 3 of the same value? This question is better to ask it in a different way. This is too simple. The one in the midterm is more complicated, a little bit. It's better to ask. I don't know if it got deleted. There was one, maybe not there anymore. Maybe it's for the final now. The other question is to ask, instead of asking this, how can I ask an equivalent question? Instead of how many cards do I need to draw to da da da? What's the maximum number of cards that I could get? And yet every value is twice, right? So the maximum value of cards that I could get with 2 values, that means for each value I get 2 cards, it's exactly 1 below the answer to this question, right? Because that's saying as soon as you add another card, you can't get only 2 values, 2 cards per value. You gotta get at least a value with 3 cards. That's something you have to realize that is true. Those 2 questions point to the same phenomena, right? Sometimes one is easier to ask and to answer than the other. In here, if I ask the other question, how many cards can I draw such that each value is represented twice? What's the answer? 26, because I have 13 values. Maximum I can get is 2 for that value, 2 for that value, 2 for that value. So 26 is maximum number of cards where every value is twice. Therefore, the answer to my question is 27, because as soon as I get one more, I have to have 3 values of some kind. Now, of course, you can do this with regional principle, right? It's the same exact principle. Be aware that those 2 questions are the same. How many numbers between 100 and 1 are divisible by 2 or 5 or 9? So first of all, how many numbers are between 1 and 100, inclusive both ends? 100 numbers, right? So how do I get, what does it mean to be divisible by 2 or 5 or 9? What kind of problem is this? What kind of technique do I need here? Yes? Indexing I need as a, as a go by with it, but I need a principle of counting. What's the principle of counting I'm looking for? Somebody else, yes.
Inclusion, exclusion.
Right. So there's the 3 sets, which are, this is divisible by 2, this is divisible by 5, this is divisible by 9. What is the question asking in terms of the 3 sets? The question is asking divisible by that or that or that means what in terms of sets? Union is asking for the 2's, union with 5's, union with 9's. This is an abuser notation. You can't call a set the 2. Okay? I can. My 2 is the numbers that are divisible by 2, but you can't. You have to say M2 or A2 or something. A divisible by 2. So the inclusion exclusion says what? If you want this, you get all the 2's plus all the 5's plus all the 9's minus 2 intersect 5's minus 2 intersect 9's minus. Now I need a little bit of number theory plus 2 intersect 5 intersect 9, right? And now the number theory said that's 2's plus 5's plus 9's minus how much is, what are the numbers divisible by 2 and 5? Those are the 10's. And then 2 and 9's? 45. I hope everybody understands what I'm writing here because it makes no mathematical sense whatsoever. This is not the absolute value of 18. This is the set, the number of how many elements between 1 and 100 are divisible by 18. And this is what? How many are divisible by? 90. Now, so now indexing might be necessary. How many numbers are divisible by 2? That's not a great way to get off by 1, you know. So 2 may not, it's better to put the numbers in front of you so you can see them. 1, 2, 3, 4, 5, up to 100. So how many, can you guess how many are divisible with 2 in there? 50. Indexing is the safer way to go by to make sure you're not off by 1. How about the fifths?
20.
9s?
11.
10s? 18s?
5.
That's where indexing will really help, right, with 18. Right? Because if I don't do indexing, I can get this off easily. 18 is not placed that nice with 100. So it's 5. How about the 45s? And 90s? Good. We've done that. What's a regular graph? R regular. Every degree has, every vertex has degree R, right? So how many, if I have 10 vertices and it's 4 regular, how many edges are there? If I have 10 vertices and every degree is equal to 4, how many edges in this graph? 4 for each vertex, divide by 2 because I counted every edge twice. How about if I want to transform this number into hexadecimal? This is a number in binary, is what in hex? Hex is 16. Hex sometimes is written 0x, right? If you see 0x, that's not a documentary about languages that don't exist anymore in Egypt. That is hexadecimal, right? 0x. I know I didn't say that, I'm saying it now. If you see 0x, it means hexadecimal. Just a notation. You can call it pineapple, but it doesn't matter. That's how it's wrote.
I'll call it.
How do I transform this in binary? The first question you should ask here is that if I don't apply any tricks, how long is going to take to transform this in binary without calculators?
Ages.
Literal forever.
That's going to go for half an hour. Do you think Virgil, maybe Virgil would, but do you think Professor Kevin Gold and Ravi Sundaram and these other more normal guys will ask you for half an hour of doing this? Do you? If you think this will take half an hour, it's like you're missing something, right? You can't possibly have 25 questions, one will take half an hour.
It's a Virgil problem.
Nah. So how do I do this in binary? Into hex? Somebody else. How do I do that? I need a trick here, right? How?
Group them as 4.
Every 4. So this is a?
1.
This is a?
3.
That's 15, right? So it's 15, same as F. You have to know A, B, C, D, E, F in hex, what they asked. How about those laws? De Morgan,
Love De Morgan.
not A and B is not A. And what happens to the or, right? And the other way, not A. How about the implications? A implies B.
Not A or B.
Is the same as?
Not A or B.
Is the same as?
B or not A.
Not B implies?
Not A.
That's called the? As opposed to the converse, which is? B implies A. That's different. Those three are the same, but the converse is different. How about the distribution? A distributed to B or C with N. How do I distribute? A and B, it's like common factors. A and B, A and C, and the ORs is in between. Same thing for N. Last thing I'm going to say, this is the logical OR, and what's the gate for it?
Kirby triangle.
That's the gate. This is the end. And what's the gate for it? It's round, right? Make sure you make it round so it not get confused. And this is not
Triangle with a circle.
Virgil, will there be if and only if?
If and only if it's equivalent means A implies B.
Yeah. Is there a logical equivalence like for algebra?
You mean a sign like this?
No, like in the same way that A implies B, it's the same as not A or B. Is there like one of those for if and only if?
No, I think you need two things. You can put the equivalent sign, but you need two things if you just do simple. I don't think there's one that's We'll see you later.
And B implies
today.
So then you can just drop it. Not the would be equivalent to
I'm worried about the proofs, but it's really just like I'm either good or I'm fucked. Yeah, same. Yeah. That's how I feel.
I know how to do. She was just talking about it. Presentations I can study for this instead. No. Why doesn't the class get pricing?
It's one of the questions in the exam says get to an infinity. You need an actual number. If it doesn't say how do you have it's kind of thing. I know it says this will be but you don't want to know what it is. I think one of the questions says, get this answer down to the pieces. That means 755,000. It doesn't say actually how I think my preference is readable, doesn't matter, but I think it definitely would be easier with a pencil. But what? No problem for us. I didn't do you look it online or you did? I have it for more than three semicircles. Then if you put a bunch of them that cover the whole circle, you can do it. You can just pick 3 of them. The problem stated there is that you have on more than 4 that cover the whole thing. You can just pick 4 of them.
So therefore, S and must apply.
Right, I didn't have time to think about it. And we figured out it's wrong. And then I think we thought about it. Here's how to fix it, but we never ended up writing it down. I don't know.
Do you want to talk it over?
I mean, I have some time, but I'm not sure if you have time.
Yeah, no, I think it's all good.
You have algorithms now?
Yeah.
And then a midterm.
Yeah. And then I have practice after that, but yeah. This
Oh,
is
that's
it so
long.
far.
We don't have time to do that now, but
Yeah.
I'd be interested.
Yeah, yeah.
Can you
I'll
come
send
to
it
office hours?
When are your office hours?
Tuesday and Thursday night, but sometimes on Thursday is my day when I can talk about fancy problems. And there are some people interested in this problem. They think about it, but nobody got anywhere yet. Maybe you did.
Maybe. We'll see.
Thursday, next Thursday for sure we're gonna have time because there's gonna be no homework. I mean, there'll be a homework, but I don't think people will have to study.
Okay.
Yeah, so either Tuesday or Thursday if you wanna come to anything, but you should submit it to me.
Yeah.
Scan it.
Or
Or picture it.
email it.
Right.
Thanks.
How do you feel about